Good afternoon, ladies and gentlemen. And in this presentation, I'm going to just application of quantum dots for biotechnological purpose. First is what is the quantum dots? The main question is that what is the quantum dots? Basically, it contains 100 to 1,000 atoms, and where the electron and hole pair are confined in a region, and very small region, and it has some properties that when confined electron hole pairs are excited with a beam of light, they fluoresce with a narrow and symmetric emission spectra. This is the main specialty for the quantum dots in advanced technology. And also, the extremely broad absorption spectra allows for the all colors range, like UV, ultraviolet to near infrared to mid infrared, and with the single excitation of wavelengths. If we excite the quantum dots with a single UV light, then we can show that the whole region of the spectrum of from UV to near infrared to mid infrared. So it has a great possibility to do something with this in biotechnological application, because today's is the demand of biotechnological purpose. This is the recent research that developed of the functional nanoparticles that are covalently linked. These quantum dots are covalently linked with the biomolecules, and especially on the peptides, proteins, and nucleic acids, and the small molecular lesions. And also, we are thinking about that at this time, the iron oxide is the most compact for the cancer detection. So we are thinking about the substitution of the iron oxide. And also the semiconductor quantum dots, it has another facility for in vitro diagnostic and in vivo of animal imaging. In vitro means within the glass, and in vivo means within the living cell. And some advantages of quantum dots: it contains the novel optical and electric properties, but I am just interested only in the novel optical properties, because my present purpose is to for tagging of quantum dots with biological molecules. So just I am interested now to the novel optical properties. And also the size and composition tunable emission, as I mentioned that it has a tunable emission properties from UV to mid-infrared region. And also the large absorption coefficient across wide spectral range, and also the very high level of brightness. This is the main factor. If sometimes it contains a whole range, but it has a low brightness. So quantum dot shows a high brightness and the photostability. And wide range of application for bioanalytical assay, living cell imaging, and fixed cell tissues labeling and biosensors. What is the physics behind the quantum dots? It's very simple. It's for the undergraduate students like that. It's a particle in a box. Here everyone knows about this, that the solution of the particle in quantum box, and using the boundary condition, we can get the energy quantization value like that, and the energy difference is between the two states, final and initial, and this. For quantum dots, it's let us consider the cadmium selenide, because I am working with really now with the cadmium selenide. It has a Bohr excitation radius, obviously fast excitation radius. So Bohr excitation radius of 5.6 nanometer, that is 56 angstroms. And so for a nanocrystal smaller than its double, means 11.2 diameter. Like if we consider an electron here, and the oppositely hold the distance between them, these like 11.2 nanometer diameter can achieve a desired distance, become a particle trap in a box. The meaning of this, like quantum dots with a small size. So size be lower than the Bohr excitation radius, like size lower than the 5.6 nanometer. It has a new facility for the getting the optical properties, because here the particles within the lower dimension of the Bohr excitation radius. The main difficulties is to synthesis. Synthesis depends on our demand. If we're going to apply this for the biological purpose, then synthesis is one kind, and if you're going to with the biosensor, then synthesis is another kind. So our purpose is to for biomolecular conjunction. So it contains 4 steps. Like first, the core synthesis. Quantum dot has a core. I will explain it next slide, that the main role of core and role of cell. And also for biocompatibility, it has to be water soluble, so aqueous solubilization. And next step is the biomolecular conjunction. The modified parameters for this synthesis is the first one, the precursors. Precursors plays an important role. How much AO will take for this synthesis, and also solvent. It's very difficult to choose the solvent because this kind of solvent is impossible to synthesis with the water. So we need to another type of solvents. And the reagent concentrations. It also main thing to synthesis like that, and temperature, more high temperature we need. But at this time, I have seen some reports in article that at the lower temperature, but I have pretty doubt with this, because at the lower temperature, main question is the stability of quantum dots. Because we need a more stable quantum dots, so at the lower temperature, maybe the stability of quantum dots like not that the higher temperatures. The first one is the core synthesis. And now people thinking to make synthesis quantum dots with the top or topo. Top is the trioxyl phosphine, and topo is the trioxyl phosphine with oxide. And main thing, I have seen the lots of journals that more than 5,000 journals that they mention that they are synthesis with the quantum dots with topo. So it's basically simple, but it contains high temperature. So at the time of experimental synthesis, there is more huge risks and need more care and more precise control. First, about 290 to 350 degrees Celsius with the top or topo, and then add organometallic liquids. What is the meaning of organometallic liquids? It means that the metal like cadmium ions with at least one bond with carbon. That means the organometallic liquids. And cell growth. Why cell growth? Because the if the core is organically passivated. If we not protect this, this will be unstable, and also the low quantum yield. I will discover that what is the quantum yield for our purpose. And the core's cell growth, like if you consider a core with the cadmium sulfide or cadmium selenide, then with the cell to protect the core. For the cell growth, we basically use a higher band gap semiconductor like zinc sulfide, zinc selenide. But I like the zinc sulfide for our recent purpose. And after that, the quantum dots for our purpose, for the biological application, the quantum dots should have to water soluble. So for biological application, nanoparticle must be soluble in aqueous, because for the biocompatibility. And also the surface ligand exchange. I will discuss it, that the exchange of coordinating ligand or topo. Like if you consider a core, then core with a cell. So if you want to tag with biological sample, then you need a ligand to tag with the biological sample. Otherwise, it will not tag with the core cell structure. So the people are, as well as that using the coordinating ligand like topo, like that. It's topo or thiol groups is the main, but we are thinking without the thiol groups, but it's very difficult because it's unstable. To stable this is still now the thiol groups are very stable ligand for the quantum dot synthesis. And also the thiol groups are attached with using the Markepto components. I like these components too much because it has a great stability in the environment. As I mentioned that it depends, synthesis depends on your requirement. So if you need the emission range like ultraviolet region or visible region, then you can use the zinc selenide or like that, but zinc selenide with manganese dope, it has some facility because it's low toxic, and people are thinking to work with this because it's low toxic, so we can use directly to human body. And also the cadmium selenide, it has an emission spectra of visible range. So if you need a wide spectral range from visible from ultraviolet to visible, then you may use that cadmium zinc selenide or cadmium selenide. Zinc selenide has a UV, and also cadmium selenide has a visible range up to. Also, you can use the cadmium telluride according to your demand. The first quantum dot synthesized by the pyrolysis method by biotic groups. As you see that here the core of cadmium selenide and with a shell of zinc sulfide and a legend of top or topo as your demand. If you radiate it with UV light, it's under UV illumination, it shows that wide total range of spectra, like first region is 475 up to 625. So it contains whole region of spectrum, like from 475 to 625. So as you need your biological demand, you can use this spectra according to your biological samples. It has some facilities, like quantum dots have strong narrow emission bands. It's a very strong emission peak, as you saw that, and also very narrow. It's not very wide. And also high quantum efficiency, more than 30 to 40%. But today, people already synthesize more than 50% quantum efficiency. And also, it is suitable to against the photo blanching and high chemical stability. This is our main problem, to stable it in this environment. It shows the quantum dot with size 1 to 6 nanometer. Now, in my recent project, I am going to synthesis with this method because already several people have used topo. So I am thinking that without topo, how to synthesize it. So I've taken some amount of for the selenide precursor, some amount of selenide, like I mentioned here, 30 milligram of 5 ml of octadens chemical component. It's alkene and C18H36. It has a long chain of carbon and hydrogen. And after this top, not topo, it's just top, triacetylene phosphine, and dissolved in selenide. And then after the preparation of cadmium precursor, just we need a temperature like 225 degrees Celsius rather than 350. So it's quite below. It's as usual, we transfer the heat and inject the cadmium ions into the solution, and it should be mentioned that within after interval of 10 seconds, you have to collect your sample. So within 3 minutes, you can collect all your samples in the test tube. So again, you have to preserve it, not in the open atmosphere, obviously, within the argon atmosphere. After collection of sample, this is a sample, you can see that it's ambient light. Its contents like light yellow to quite dark red. So under the UV radiation, you can see the total range of spectrum. First one with the blue, so blue to up to the quite red. So it has a size-dependent optical properties. Now, the main problem is to measure the sample, basically the spectroscopic analysis. As we know, the spectroscopy measures the absorption or emission of energy. It's very simple method because already the physics behind the spectroscopy is contained in the graduation level. It's just jump to one level to another level, and we'll measure the absorption intensity corresponding this. This is the the frequency or wavelength, and you can see the absorption intensity, the peak corresponding any sample is the peak according to their state. But right now we are just interested only this region, that ultraviolet and the visible region. So it contains that the electronic excitant. For our purpose, we use the UVBI spectrometer. You can see the transition of electronic energy from one level to another level. You can measure by UVBI spectra very easily. There are 4 types of transition. The first one, you can see here that the transition between D and D state or AFF transition. Second one, the adjacent atom, from one atom to another, one to another. And third one, from one to another state. And the fourth one state to another state. We are interested only in the fourth one because it's electron from valence band to conduction band. This is so the exact nature of the semiconductor for our purpose. So it is a powerful technique for measure the interband electron transition for semiconductors. To measure the luminescence, it's sometimes it's called the photoluminescence, sometimes it's called the fluorescence, but the photoluminescence. Oh, sorry. The photoluminescence or fluorescence is the same as the emission light, and it's also very simple. As I mentioned that the quantum yield, it's first one, if you inject the electrons by excite with the UV light, the electron jump to the excited state, to the ground state, and you will measure to the emission spectra. And it's a photoluminescence and fluorescence. Photoluminescence is used for inorganic materials. Fluorescence is used for generally organic materials, but it has not the difference because it's just term for using how to measure your sample. For our case, you see that first one is green and the last one is red by color under the UV radiation. So if your sample with the green color, you will see the spectra, absorption spectra like 520. It's for the cadmium selenide. And if your sample is corresponding to red, then you can see that spectra around 630 like that. And corresponding photoluminescence, you can see that green is green peak, both are same, quite same, a slight peak difference due to the non-radiative recombination, and also for red or slight peak shift for their positions. As I mentioned, according to our demand, we need to synthesis. I mentioned here that every component, quantum dots, still right now, but we are right now we are interested only this cadmium selenide or cadmium telluride for our present purpose, and also the cadmium sulfide. But I'm not interested too much cadmium sulfide because cadmium sulfide is very toxic, and cadmium selenide with the core of zinc sulfide. You can see the lead selenide contains the near infrared region to the mid infrared region up to more than 300, more than 3000 nanometer wavelength. Main difficulties for quantum dots is toxicity. When you're going to apply with the biological cell, it's due to very toxic, so it can destroy the mitochondria, or so due to a large stress. So we have to stop the toxicity of quantum dots. The main remedy, as I've seen, that the cadmium ion is the basic main role for toxicity. So protect the cadmium ion by using any kind of this. First one, surface coat of cadmium, like cadmium selenide, coat with the zinc sulfide. You can trap with the cadmium ion inside the core. Second one, use gelatin. If you use the gelatin during the production of cadmium, any kind of cadmium telluride or cadmium telluride, then the toxicity will be reduced. And or also you use the another kind of tripeptide. Otherwise, you can use the peptide to reduce the toxicity of quantum dot. Besides this, I am interested with another project that contains quantum dots with some ferrofluid materials. But as you see that ferrofluid materials, its volume 27%, and the quantum dots volume less than 1%. If we mixed with them, then what will happen? We see that under the UV radiation, it can show a wide range of spectral, and it has a quite good capability to interact with the biological species. Like this, addition of the fluorescent species less than volume 1, and you can see that spectral range up to this color. And also the optical microscope image for the ferrofluid material containing quantum dots. It shows a quite spherical but not uniform, but maybe we can use some filter for this. For biocapability, we need the spherical quantum dots. Otherwise, spherical quantum, other than spherical, it's not very well capable to interact with the biological element. As you see that we measured the fluorescence intensity of quantum dots for containing ferrofluid materials. The first green line, the first one, quantum. Let us consider quantum dot concentration of C. So first one, you can see the slope 0.153. If you double the concentration of quantum dot like 2C, then slope also double. If you triple it, so slope also triple. And so we can say that the intensity of fluorescent spectroscopy, that it depends on volume of droplet and also the quantum dot concentration. But interestingly, that after 2 days, due to the aging effect, you can see the slope slightly reduced, because first one slope 0.153, but later the slope is 0.13, so slope is going down. So main question, as I said, that the stability of quantum dots. We should care about the stability of this kind of sample. Also interesting quote, it's not my work, it's published in this journal, that quantum dot containing cancer cell. Its red Steinberg cells can distinguish by their red outline, and also a funny quote, the researchers describe finding the cells like finding a needle in haystacks. I mentioned about the haystack meaning. And also I am doing another work with Professor Condorcet and Professor Alexander Osipo, that to develop the rapid lateral flow test. As our today, we need a rapid test like pregnancy test or something not to go in clinic. So we need a rapid test. So we are just thinking about to test with quantum dots with antigen like that. Sorry. So clinical purpose, we need a rapid, simple, and inexpensive. It should be mentioned that inexpensive. Because if it's expensive, then we will go to the clinic. And also the lateral flow test provides as a format, and it's quite confirmed test that it's positive or negative. But for patient case, it's quite not in very good position, because I know few kits which can track very well, but after that we are not sure the result is positive or negative. So as our design, we design like this, it's by discussing with Professor Kondakopse and Professor Alexander Osipov, that we are thinking about only this part, because this part contains gold conjugate pad. As you know that gold has huge market demand and high price. So if you reduce this with the quantum dot with the low price, and also if we think about that after multiple use, not by only a single use, so it will be great. I think so. And it contains some parts like sample pad. It's made by cellulose. Conjugate pad, as I mentioned, is the first one is the sample pad, and also it's the gold one. Conjugate pad made by the any kind of polyester. Detection conjugate today is gold. So we are thinking to substitute of gold with the quantum dot, and also the multi-purpose use by single stick. And just I described the several parts of our laboratory floor. Day before yesterday, we presented our work in Tambov State University, and I went there with one of my students, Sargi, and we present there our work, and it's something about our presentation. And it's something about the, beside this, I'm working with Sargi, with quantum dots, not in quantum dots, but it's also in low region with cadmium sulfide, reducing the toxicity with adding some kind of doping like copper, or I'm thinking also next time with manganese, like that. So in conclusion, we may say that after a few days, we'll be substitute gold with quantum dots. And also, our problem is that to make stable quantum dot, which is environmentally more stable rather than now position. And thanks for your attention, everybody.
What papers will you have?
Yes, right now in my recent project, we have just finished two papers, and I submitted only one to Dr. Kuznetsov, and he under correction. Maybe within 10 days I will communicate with 2 journals. So it just basically, you know that I need some imported chemicals. So that's why I spent quite time for that chemicals.
Now you have.
Right now, maybe it's in Moscow, because I'll get within 2 or 3 days. It's suppliers told that we'll deliver within 2 weeks, but already they spent more than 1 month.
Is there some technology to clean and to remove, to take away the quantum dots from after the analysis? Because they can
to neutralize them.
Yeah.
Yes.
Contaminate that they do not contaminate the body.
Yes, maybe you can use it like that. It has aging effect. So after few days, it will destroy automatically due to the aging effect. So you can use it, the recent synthesis quantum dots, and after you can use it to the body after a few days, due to because body has open atmosphere, so it will be aging effect. It will be going large, and it will destroy itself.
And what density of these quantum dots is necessary for the analysis?
It's not density. It's like size. Size is less than Bohr exciton radius. So it's not exact size like 10 nanometer like that. So for cadmium selenide, less than 5.6 nanometer.
But how many?
But how many? How many of them you need for your medical tests?
It depends on your medical sample. If you give me some peptides, firstly I will measure it the fluorescence spectra. If the spectra write 500 nanometer, then I am going to synthesis with quantum dots with the fluorescence spectra around 500 nanometers. So it depends on your sample.
Average size.
Average amount of your
Yes.
How many particles do you need?
How many particles do you need to make your test?
How many particles?
Yeah, to observe, to detect the signal.
What
Oh.
is the sensitivity of
Yeah, but
You see, it's very, if you give very low amount of, if you give me just 1 ml, then it's okay for synthesis, for characterization. So less than 1 ml is also okay. Just
all optical methods.
all optical measurements, yes.
That's why you don't need a bigger.
No, we don't need the bigger amount. Yes. It's not like component, like weight 1 gram, 0.5 gram, not like that. It's you have biological cells. Then if you give me the cells, then I can measure it by fluorescence spectrometer, and the fluorescence spectra of the biological cell. Then I will synthesize in quantum dots according to your biological cell.
Спасибо.